In the last video, we talked about the three different definitions we use in chemistry to describe acids and bases. In this video, we'll focus on Bronsted-Lowry acids and bases, and how we can draw the reactions between them. As a reminder, Bronsted-Lowry acid is a species that can donate a proton or a hydrogen ion. A Bronsted-Lowry base is a species that can accept a proton or a hydrogen ion. The flow of a proton from acid to base can be described as a flow of electrons, a pattern we will be able to apply to Lewis acids and bases. If we draw out a generic acid, HA, and specify that A has 3 lone pairs, we should be aware that the bond between H and A is a covalent bond and is characterized by the sharing of 2 electrons. We should also be aware that no matter what element A is, it'll be more electronegative than hydrogen. Therefore, if the bond between H and A is broken, where would the 2 shared electrons rather go? The less electronegative hydrogen or the more electronegative A? If you said A, you'd be correct. To show this, chemists like to use curved arrows to show that the electrons from the bond between H and A will end up on A. Therefore, we would end up with our element A alone, now with an extra lone pair and a negative formal charge. In these types of reactions, acids do not exist alone. Bases are required to cause this bond to break. To show that, we can use a generic base B-. When the bond between H and A is broken, one of the extra lone pairs on B would reach out and grab the newly single hydrogen and form a covalent bond. This would form HB, with B now having a neutral formal charge. Let's try this with real acid-base reactions. We're going to explain what makes these 2 species acids and bases respectively, but for now, take my word for it. If we drew out a reaction between hydroxide and hydrogen chloride, we'd be able to define HCl as our acid and OH- as our base. Therefore, the bond between H and Cl would break, and the electrons would move toward the more electronegative chlorine. Hydroxide would use its extra lone pair to scoop up the now free hydrogen, and would become H2O, or water. I want to congratulate you. With what, you may ask? Well, this diagram we drew out is called a mechanism. Chemists use mechanism to explain reactions between species. Mechanisms aren't just used for acids and bases. You'll be using mechanisms to describe tons of reactions throughout the course. Back to our example. We said that hydrogen chloride acts as an acid, and hydroxide acts as a base. For a second, read this equation from right to left. In that case, water becomes our acid, as it donates a proton to become hydroxide, and chloride acts as a base, accepting a proton to become hydrogen chloride. We call the backwards acids and bases conjugate acids and bases. The acid in a reaction will become a conjugate base, and the base in a reaction will become a conjugate acid. Drawing mechanisms does not come easy, so remember to practice them by using my free worksheets and answer keys below. If you have trouble, check out my explainer videos for the worksheets, also linked below. In the next video, we'll draw out mechanism for Lewis acids and bases, as well as define acid-base and conjugate acid-base strength.